For this last video, I'm moving to PowerPoint because I have some slides already made up here. First, we're going to talk about auxiliary complexing agents. So the reason these are important is that we've seen that high pH is good for EDTA titration. That means we have a large K value and the complex is favored. If we get to a low enough pH, the complex is not favored and we don't get a good, a good titration reaction. So generally, EDTA titrations are done buffered at high pH. And so when we do this in lab, we use an ammonia buffer at a pH of around 9 or 10. And that lets us get a very large value of Kf prime like we want. So that's good for EDTA titration. The problem is a lot of metal ions precipitate with hydroxide. And so, of course, a high pH means a high hydroxide concentration, which means that you may be losing your metal ions to precipitation in your solution. So that's obviously no good. So what we use is what's known as an auxiliary complexing agent. So an auxiliary complexing agent is something that will bind to the metal that'll prevent it from reacting with the hydroxide and precipitating, but is bound weak enough that it'll give up the metal to EDTA so you can actually do your titration that you're interested in doing. Here's some structures or some specific auxiliary complexing agents that are commonly used. One simple one is ammonia, which is good because it's often used in a buffer to have that high pH that you want. Tartaric acid, so this is another chelating agent where it has these carboxylic acid groups here that can bind to the metal. Same thing with citric acid, where now we have 3 carboxylic acid groups. Right, so these are agents that we can add that will complex to our metal but still give it up for EDTA, but prevent our metal from precipitating with hydroxide. So this is a common technique used to get around that fact that many metal ions precipitate with hydroxide. The other thing that I want to just finish up with is how do we actually observe the endpoint? The most common way this is done is with metal ion indicators, similar to how we have acid-base indicators. So these are colored indicators that when they complex to metal ions, but their color changes when they are not complex to metal ions. So these are themselves complexing agents, similar to how EDTA is. So similar to how acid-base indicators are themselves acids and bases, metal ion indicators are themselves complexing agents, just like EDTA is. And so similar to our auxiliary complexing agents, these need to give up the metal ion to EDTA. And similar to EDTA, the protonation will affect color, right? So these are acids and bases as well as complexing agents. So this is a table from your textbook that has several of these indicators. Calmagite is one that we use in lab. Areochrome black tea, which is very similar. Murexide, xylanyl orange, pyrocatechol violet, right? We have these different things. So one that we do in lab is manganese calmagite reacts with EDTA to form manganese EDTA, and then the calmagite is freed. And so that's what's happening here, is that the color changes depending on whether it's complexed or not. So we see here on the far right, we have color of the metal ion complex. And for example, for murexide, it depends on what metal ion it's complex to, but generally they have one color when they're complexed and a different color when they're free, and that color depends on which form protonation it has here. All right, so just to see what this looks like in practice, this is a magnesium calmagite solution during EDTA titration, showing A is prior to the endpoint. So this is where the magnesium is complexed with our indicator, a small amount of our indicator. Point B is where we have a mixture of the two, and that's the endpoint that we're looking for, where we have basically all of the EDTA has reacted with all of the magnesium, and so we're starting to lose any calmagite complex that's there. And if you go too far, all of the calmagite is now not complexed and is turned to this blue color. And so this is how we observe the ends of of EDTA titrations. Similar to acid-base titrations, we have this color change that we're looking for. Other ways to monitor EDTA titrations include using a pH electrode. If you don't buffer your EDTA titration, the pH will change as you do the titration, or to use a mercury electrode, which is a way of monitoring metal ion concentrations. but by far most common is to use an indicator. So this concludes chapter 12. This is the end of talking about titrations. So moving forward in class, we're going to move on to talking about electrochemistry and using electrochemistry for analytical chemistry, and then to spectrophotometry as another specific analytical tool that is commonly used.